Welcome to this lecture series in real analysis. In this lecture, we'll look at a certain theorem about convergent sequences, which we will generalize in the next lecture perhaps, but it illustrates the importance of Cauchy sequences, which is why I decide to do this somewhat special case of the more general theorem. Anyway, so let's recall what we need before we get into the material. So we will need to, of course, know about convergent sequences and this fact, which is called the Bolzano-Weierstrass property, that every bounded sequence of reals has a convergent subsequence. We will need to know about the algebra of convergence, which means what? Which means the following, that things like this, you have limit of the sum of two sequences is the sum of the limits, provided an and bn are both convergent sequences, and such like. So you have limit of product is product of limits, again assuming the two sequences in question are convergent, and so on. Okay, we of course need to know about Cauchy sequences. So what are Cauchy sequences? We say that a sequence, call it xn, of real numbers is Cauchy if for all epsilon greater than 0, there is some natural number n such that whenever we have two indices exceeding or are at least capital N, we have their distance is at most epsilon. So the points of the sequence come closer and closer to each other. That is the idea. And we showed that convergent sequences are exactly the same things as Cauchy sequences. Okay, so with that, we can proceed. Here are some problems for practice. This one is marked as star, not because it is hard, but because I'm going to use it at one point. This is a very simple fact. And this one is marked with dagger because I believe this is actually a little bit harder than the rest. I intended to cover this as an example, but I decided against it. If one wants, then you can write in the comments so that I can make a video on this separately. Or maybe I will make a video on this separately, I haven't decided. All right. So let's start. So fix two real sequences such that both are convergent, and let's call A as the limit of the first one and B as the limit of the second one. Define a new sequence, dn, which records the distance between the nth terms of the two sequences. Then we claim that the sequence dn also converges, and in fact it converges to this difference. So the proof is very simple, but let's just see intuitively what this is saying. We have a point A, we have a point B, and the first sequence converges to A, so ultimately the points of the sequence kind of hover around A, and the points of the other sequence hover around B. So their difference will come closer and closer to this distance, right? Because the points of AN are coming closer and closer to A. Points of Bn are coming closer and closer to B. So their distance will be, of course, closer and closer to the distance between A and B, and that's it. But let's maybe write one line. This is where we will use the star mark problem. So, so what did the star mark problem say? It said that if we had a convergent sequence xn, then this sequence, which is obtained by taking the absolute values of every entry of the sequence, is also convergent, and the limit is the absolute value of the limit of the original sequence. So now, since an and bn are convergent sequences, their difference is a convergent sequence because algebra of convergence. We proved algebra of convergence for sums, but of course it also holds for differences. So this sequence, the difference sequence, meaning just this much, this sequence is convergent. And now by the star mark problem, we can immediately say, or maybe to illustrate or elaborate on it a little bit, write xn as this thing. Then we know xn is convergent because of algebra of convergence. And now the limit of the absolute value of xn, which is same as the absolute value of xn is same as dn by definition, is, by the star marked problem, equal to this thing. And now maybe I'll write one more step. Now just use the definition and the algebra of convergence. So limit of xn is limit of an minus limit of bn. Limit of an is a, limit of bn is b. Okay, very simple. The second lemma. So suppose we have two bounded real sequences. Then we are saying that there exist strictly increasing natural numbers, or there exists a sequence of natural numbers strictly increasing, such that the corresponding subsequences both converge, right? This is saying a little bit more than the Bolzano-Weierstrass property. The Bolzano-Weierstrass property says that starting with any bounded real sequence, you can find a convergent subsequence of it. So both A and B admit convergent subsequences, of course. But what we are saying is that you can kind of choose a simultaneous subsequence which converges. So there is one increasing sequence of natural numbers such that if you pick out the corresponding subsequences, one from this and one from that, both of them will be convergent. So there is one such thing which makes them simultaneously converge. All right, but this is not hard, and you can write down a proof of it by two applications of Bolzano-Weierstrass property, and that is what we will do. But to do this, we will resort to the other way of looking at sequences. Rather of thinking sequences as an infinite list, we will think of it as a function from naturals to reals, and that will just help us write down the proof in a more neater fashion. But I encourage you to write down your own proof before we look at this one. So, okay, so think of an as this sequence. I will not write full sentences. So this f denotes the sequence an, and let's say g denotes the sequence bn. So just to beat it down, let me maybe write it somewhere. An is f of n and bn is g of n. Okay. Now by the Bolzano-Weierstrass property, S has a convergent subsequence. Which means what? Which means there is a strictly increasing function phi. There is a strictly increasing function phi such that this composite, which is of course a sequence in reals, is convergent. So this composite is a convergent sequence. This is by Bolzano-Weierstrass. All right. Now we are not saying that here this sequence that you get, we are not trying to say that G composed with phi is also convergent, but it is a subsequence of G. It is some subsequence of G. So just to recap, we started with A and B, which we are denoting in the function language f and g. By Bolzano-Weierstrass property, this has a convergent subsequence, so there is some strictly increasing function phi such that the corresponding composite is convergent. We have recorded the convergence here. And we can form the corresponding subsequence of this guy, which we can't say that this also converges. But this is also a bounded sequence of real numbers, because this is a bounded sequence of real numbers. Any subsequence of a bounded sequence is a bounded sequence. So now apply Bolzano-Weierstrass to this, and therefore there is some strictly increasing function psi such that the corresponding composite is a convergent sequence. So G composed with phi composed with psi, which is of course same as G composed with phi composed with psi, this is convergent. We have applied Bolzano-Weierstrass to this sequence. Okay, but now we can consider the following subsequence of F composed with phi, which is obtained by composing it with psi. So this is a subsequence of F composed with phi, but this is a subsequence of that. This one converges, and hence this one also converges. Any subsequence of a convergent sequence is convergent, and in fact it converges to the same limit, but that is besides the point. So now look at this. We have a strictly increasing function from naturals to naturals, this chi in the diagram, which when composed by F yields a convergent subsequence both for F and G. It's the same guy that appears. So there is a subsequence of F, or rather, I mean, if you just define N1 as the image of this guy, image of 1 under this guy, N2 as the image of 2 under this guy, N3 as the image of 3 under that guy, you will see that both of these sequences are convergent. So the more traditional way of writing this proof is the same thing. You pick a convergent subsequence of this guy, then you create the corresponding subsequence for B, and then you extract another subsequence of that thing, and then it's the same proof, but writing it in this lexicographic manner is, I shouldn't say lexicographic, but in this manner is will involve triple subscripts. Double subscripts already are appearing, but once you extract a further subsequence of a subsequence, you'll have triple subscript, and that starts looking not just ugly but intractable. So this language saves the day. And with that, let us proceed to the main theorem, or the main result of this lecture. So fix a bounded real sequence. And now here is the hypothesis. Assume that there is some real number x such that whenever this thing is convergent, once again, we have a bounded real sequence. Assume that there is some real number x such that whenever a subsequence of xn converges, or whenever you pick a convergent subsequence of the original one, you find that its limit is actually x. So what are we hypothesizing? We are saying fix a bounded real sequence with the property that all convergent subsequences of it converge to the same limit. We are not demanding that all subsequences of it converge, because that is same as demanding that the sequence itself converges. We are not demanding that. We are demanding that if a subsequence converges, it will converge to the same point. All subsequences which converge to the same point. Not that all subsequences converge. But as a consequence, we will show that actually all subsequences converge. In fact, the original sequence itself converges, and its limit is the same point. So one should appreciate the difference between asking this statement and asking that every subsequence converges to the same point. We are not saying that every subsequence converges to the same point. We are saying every subsequence that converges to the same point. Okay. All right. So our goal is to show that actually the original sequence converges, and the way we will approach it is by showing that the original sequence is a Cauchy sequence. Okay. So we will proceed by contradiction. So suppose not, then the original sequence is not convergent, and hence equivalently it is not Cauchy. Therefore, this is not a Cauchy sequence. Okay. Now, using the definition of Cauchiness, or the contrapositive of it, therefore there exists epsilon. There is some epsilon greater than 0, such that for each I, we will use the index I, which looks a little ugly, but let's use it, such that for each I, we can find two natural numbers, pi and qi, both exceeding I, such that satisfying. Don't want to use two such that's. So we'll say satisfying this inequality. So this longish statement is just immediate from this. In fact, this longish statement is exactly the same as this. So let's be very, very clear about that. And now what we have is, this P1, P2, P3 and Q1, Q2, Q3. But here is what I want to say. One can be very, very formal here, but let me just maybe say and ask you to convince yourself that one may assume that this is a strictly increasing sequence of naturals, and this is also a strictly increasing sequence of naturals. All I'm saying is that here in this statement, we are saying there exists epsilon greater than 0 such that for each natural number I, one can find pi and qi greater than I, satisfying this condition, and also demand that p1, p2, p3 ... is a strictly increasing sequence of naturals, and same for q1, q2, q3. So maybe I'll write it that way. So there exist satisfying two conditions. One is what we have written here, satisfying this, and these two things. So let me ask you to convince yourself why this statement implies this statement. Okay. So with that in hand, to define x, let me use the symbol. What's a good symbol? Okay, so define, maybe I'll write AI. I mean, I don't have a choice, perhaps. Define AI as x pi and bi as x qi for all I. So what have we done? Because of this condition, or this fact, A1, A2, A3 ... is a subsequence of original one, and same for this. Both of them are subsequences of the original thing. Okay. And since this was a bounded sequence, both the sequences, so the sequences, or let me say thus, this one, maybe notation has to be, I want to be a little bit careful about the notation, so let me write, yeah, there's nothing wrong with it. So thus this and that are subsequences of the original sequence xn. But forget about xn for the moment. We have two bounded real sequences, and by what we just learned in the previous slide, we know that we can extract a quote-unquote common subsequence of both of them, both of which converge. So all I'm saying is that by the previous theorem, we know that we can find such that both of these guys are convergent. Right? This we have from the previous proposition. And now we have, what is the limit of this guy? This is a convergent sequence, but what is the limit of it? The limit of it is x. Why? Because this is a subsequence of that, which is a subsequence of that. And hence this is a subsequence of that. A subsequence of a subsequence is a subsequence, if that makes sense. So this is a subsequence of that, and by hypothesis, every subsequence that converges to little x. So this converges to x. By the same reasoning, this also converges to x. Okay? And therefore, this limit is 0. This is where we use the lemma 1. So this is a convergent sequence, this is a convergent sequence, both have the same limit. So the limit of their, the difference of their absolute value is the absolute value of the difference of their limit, but since they have the same limit, this thing is 0. But this minus that is greater than epsilon. Because what is ank? Ank is, this is equal to x sub p sub nk. Looks ugly, but that's what it is. And this is equal to x sub q sub nk. And by this statement, that is at least epsilon. And hence this thing, which is always greater than epsilon, converging to 0, is a contradiction to the fact that epsilon is positive. So slightly long-winded reasoning, but it's not, it's kind of a follow your nose argument. Once you decide to use the Cauchy criterion, nowhere in the statement the word Cauchy is present, and this proposition perfectly makes sense without even defining the notion of Cauchy sequences. But the fact that Cauchy sequences and convergent sequences are exactly the same things helps us solve this. So the point of, or the usefulness or the convenience afforded by Cauchy sequences is that it kind of frees us from dealing with the limit of a convergent sequence. You have a sequence. To decide whether or not it is convergent, you can kind of work within the sequence. You don't have to ask for some real number to which the sequence converges. You can kind of work within the sequence, if that makes sense. Okay, so that's all for this lecture. As usual, like, comment, share, subscribe, and I will see you next time.